Okay, hi everybody. Let's just start. May I ask you guys turn on your camera, please, so I can see you. Thanks. The more, the better. Okay. So if you remember, in the last lecture, we started going through different types of instructions in both LC3 and MIPS. We started off with operate instructions. If you remember, mainly the operations that gets executed in the ALU, right? Such as add, not these logical or arithmetic operations. Um, Today, the plan is to finish more and cover all type of instructions, hopefully. Um, Specifically, we'll talk about data movement instruction and addressing modes. These are important types of instruction. And later on, we have more variety of instruction that basically enable you to program more interesting or more variety of code and logic, so you are able to program, to start writing programs. Specifically, from next week, we'll discuss assembly programming, and this is part of the course where you should be able to do some homework, some projects with assembly, so you can write program, debug program, test, and solve some problems. So before we start, do you have any questions specifically about the grades and everything? I think it was clear for you guys. You should be able to see the answers for your quiz, first quiz, and hopefully from next quiz you do better. I expected actually more from you. So try to do better. And as I said, I do not consider the lowest score for your final grade. So try to improve as we go and learn to be able to learn about computer architecture and be able to program like interesting assembly code and so on. Is there questions in the chat? Yeah, I hear your feeling. Try to do better. I'm sure you should be able to do better. Probably some of the mistakes, I mean, maybe it was the first time getting used to this, but I expected you to know more about this, because these binary stuff, these number systems, I expected you to know before we start this class. But maybe that was also part due to the grade scope that we use. You needed more time probably to get familiar with how grade scope work. But anyway, I expect you to do better, get better score. from next time. Miles, what is your question? So if you have if you want your last question to be regraded, you can certainly do. As I mentioned, you can request it through Gradescope. I sent you some screenshot how to request that, and the TA will regrade that, but specify some notes why you believe that something is missing. Yeah, there might be some mistakes, so please check. And if you believe that we made a mistake in grading those, let us know. Certainly, we will happy to do that. Okay, let's start going through these instructions. LC-3 has specifically 7 data movement instructions. You saw already LDR previously, and the format of these instructions, these data movement instructions are similar. As you know, this you have some opcode from bits number 12 to 15. You have destination register or source register, depending on the type of instruction that you have, and you have some address generation bits from bits number 0 to 8. And depending on the addressing mode, you can interpret this differently. And you have 4 different ways of addressing modes. You have PC relative mode, indirect mode, Base+Offset mode, and immediate mode. You already saw that, not all of them, couple of them before when we discussed the formatting in general, but now we are going to discuss most of them, all of them. In MIPS, there are only 2 types of data movement, Base+Offset and immediate modes. These are the 2 basic type of data movement or addressing mode for load and store instruction. So these data movement instruction are type of instruction where you want to load some data from memory to register, or you want to store some data from the register into the memory. These are basically the functionality or semantic of these instructions. So PC relative addressing mode, for example, in LD and SD, LD is for load and SD is for store in LC3. So this is the formatting. You have 4 bits for opcode. You have 3 bits for either destination or source, depending on whether it is load or a store, and you have 9 bits of offset. And you know that again in LC3 we have only 16 bits for the whole instruction. So you have 9 bits for the offset, and these are a specific code for load and store. You know that, and the semantic of load is very simple, right? So you have one specific address in PC, and this PC you already know now. Once you reach this instruction, your PC is pointing to the next instruction, right? It's already incremented. if you remember in the cycle, the incrementation of the PC happens in the first step, right? So PC is pointing to the next instruction. You have one offset, 9 bits. So in order to go into the memory address, so this is the semantic. You need to, this instruction says that go to the memory address, which is located PC plus offset. Offset is already 9 bits. You need to extend it to become 16 bits because PC is already 16 bits. So you need to add 2 16 bits. That's why you see sign extension of PC offset. And then you go to the memory address of this specific address, PC plus sign extension extended of PC offset, and then retrieve whatever you find there and load it into destination register. So for LD, for load, these 3 bits specify the destination register. For ST, for store, these 3 bits specify the source register. You want to store whatever you have in the source register, one of these 8 registers that you have in LC-3, and store it in location of the memory, which is specified by PC plus sign extension extended of offset. That's very easy, very straightforward semantic. And these 2 operations, as I said, are used for communicating data between register to memory and memory to register. Any question about this? So for example, this is one line of assembly code says that load 0x1AF into R3, right? So this is the second argument is the offset. And we have a PC, so we need to go to the memory address located at PC plus this number and load whatever you find in the memory into R2. So this is, you know that this is hex encoding. Each and you know how to interpret these numbers, right? Each of these numbers represent 4 bits. Again, this is how it is encoded in the machine, right? So you have bits number 0 to 8 representing the offset. So to correspond it, the first, if you consider the first on the lowest side, right, the first 4 bits, this is what it corresponds to F. And then you have 1, 0, 1, 0. This is correspond to A. And the last bit is correspond to 1. So you have 9 bits representing the offset here. So you can make the correspondence between these. And then here, since it is load based on the opcode, this is destination register. So referring to register number 2. And this is the way how it is implemented in the machine. So you have, so you need to do one addition, you need the offset code, bits number 0 to 8. You need to sign extend this. Once you sign extend it, you add it to the PC. So you need one add logic here to add this 16 bits number and load it to MAR. That's how you can retrieve the content of memory. Again, wherever that you need to access memory to retrieve something from memory, or you write something to the memory, you need to write the address into MAR. That hopefully you remember. Memory address register. This is a specific register where it is used for accessing memory. So once you add this 216 bits number, you load this into MAR, and again, in order to reiterate that, the number refers to a location in the memory. This 16 bits number is a pointer or a location of a memory. So you load it to MAR. This is the first step. Once you load it into MAR, you can access the memory, read from the memory, and then write the content of the memory into MDR. Basically, this is what's happening in the second step, right? So the second step, you load the content of the memory at that particular location and write the content into MDR. So you have the number into MDR, and again, to repeat that, this reading from memory might take several cycles, and depends on the speed of the memory read. So you read and load the content into MDR. MDR contains the data, contains a data point which was located at that particular location in the memory. Once you have this in the MDR, then you can load this data into destination register, which was located at R2. This is what the code says. So R2, you see that in the register file contains now the content of the memory, content of the data that was located in that particular memory address. Hopefully this is clear, very simple. This is how it is implemented in LC-3. And the memory address is only 256 plus 256 to minus 255 location away from the instruction, from wherever the PC location is. Do you know why? Can anyone point to why this is the case? Why only we could point to like plus 256 to minus 255 location away from the current instruction? Limits of the binary system we use. Can you elaborate more, Bobby? What's the limit here? So 256 is, yeah, but why? Yeah, I know, like 2/8 is 256, but why specifically? What was your reasoning? Can you elaborate? You're getting there, Ross. Bobby, Bobby, do you want to elaborate verbally, if you could? It doesn't matter if you're wrong. That's fine. We want to learn why that's the case. Yeah, but can anyone verbally wants to elaborate so others can listen? R0 to R7, not really. I would like to hear what's the reasoning behind this.
Sure. Can you hear me?
Yes.
So if the PC offset is 8 bits, it can be a maximum offset of 1 in each of those 8 bits. So 256. Although that would be 255, so I might not quite be there yet.
Actually, it's 9 bits, right? It's number 0 to 8, right?
Oh yeah, that is 9. So 256 plus a sign. Is the 9th bit like a sign?
That's right.
Yeah.
So if you
I'm on the same
consider
page as Bobby here. It's signed.
yeah, it's a signed number, right? And you need to interpret it given two's complement, right? Interpretation of signed numbers, right? Uh, so in two's complement, given n number of bits, here like it's 9 number of bits. Um, the maximum, so basically the minimum is minus 2 over 9 minus 1, all the way to 2 over 9, 9 2 over n minus 1, right? So that's a range that you could cover in two's complement interpretation of signed number. And that's basically uh, the only capacity that you have in this instruction to offset from the PC, right? Um, so you cannot go beyond these memory location wherever the PC are. So you only have this range in order to move away from the current instruction. And in total, you know that in total we have 16 bits for the total instruction. We need the opcode, we need the destination register or source register. So we already have 4 and 3 for them. So it's only remains 9. So that's the limitation that we have to live with it in this encoding. Okay. We have also indirect addressing mode, which is it's one of interesting addressing mode here with load indirect and store indirect. These are useful when you want to have indirect like a pointer when you have a location of a memory stored in memory already. So essentially, you want to access part of the memory. In that part of the memory is not the data, but another address that you need to refer to that address in order to retrieve the data. This is useful um, for pointer implementation. So you have similarly opcode. This is for LDI. This is for SDI. Destination register, source register in SDI. And this is the semantic of LDI and SDI. So in LDI, so you need to similarly to previous one, but now you see two memory location here. So you need to first go to the location of the memory, which is located at PC plus sign extended PC offset. Go to that memory location, retrieve whatever you find out there, and then access the memory of the location that was located there. So this is indirect memory access. You need to retrieve, you need to access memory twice. That's the way how we can interpret it. For the store indirect, similarly, you store the content of your source register into the location which is not um, indicated by memory PC plus sign extended, but you need to you need to go to the location that twice, right? So after you read whatever you find in memory PC plus sign extended, you need to go to the target location and store the content of source register there. So hopefully it is clear. Like this is one example, LDI. You see the offset and the register, destination register in this case is register number 3. And once this is the offset, this is the encoding. And this is the way how it is implemented. Very similarly, you do the same. You retrieve the offset, you add it to PC, you load this address after you add them up into MAR. Next, you go and read from the memory whatever you find after you access, after you find out the location. Once you read it, you're not going anywhere. You need to again load the content into the MAR again. So basically, again, you need to, after you retrieve the content from the memory, you need to load MAR again this twice, and then once you read the content of the new location, then you can load it into destination register. So in this way, you load two numbers into MAR. Once after you add these two numbers, and once after you retrieve the content of the first memory address. And the actual data is located when you address the memory for the second time with the second address in MAR. Is there any question about this?
So you don't need to like run LD on this. It would just be LDI and like because I was thinking like the offset could be more than 256 because you need to do LD after you did LDI, and like you could have like 2 offsets or like more than that, but it would just be it's all in one operation still, and it's still like the same maximum offset or minimum, if that makes sense.
Why we need to do LD here again?
No, I was just asking, is it all in one operation, or like you don't need to do LD? It's just all
No, no,
it's all
it's
okay.
all. That's a good question. No, all in one operation. Like LDR is one atomic operation, right? Um, but in this operation, you need to access the memory twice, or you need to load MAR twice here. Um, yeah, yeah, and you know that now the address of the um, whatever it was located in the memory address could be anywhere in the memory, right? So now it gives you the flexibility uh, to not only move like on the on a limited offset from the current instruction due to the 9 bits 9 bits encoding of the offset, but you could like store wherever you want to go in that memory location, so you have the flexibility to go anywhere in the memory. The third addressing mode is base plus offset. Load register and a store register. Here you have slightly different encoding. You have 4 bits for opcode. You have again 3 bits for source or destination register. You have also a base register, and you have only 6 bits for the offset in this case. But you know that like these base, so the the location, because you use a specific register, you have more flexibility to move around memory in this case, because you are using the content of a register as a base location. So you are not, in this case, you are not limited, because in previous instruction, if you remember, you were limited only by PC by default, right? Based on the semantic based on the semantic of the instruction that we had before, right? So here, like for load, based on semantic that we had, we were using the location of the PC as one of these arguments and add it to the offset, right? That was by default. You were limited PC plus offset, but in this case, the base location could be specified by your base R in this encoding, so you have more flexibility in that sense. So you load the content of memory, in this case, instead of PC, again, instead of PC, you have base R. This is 16 bits of location plus sign extended offset. Now you have 6 bits here. This is typically useful for addressing an array, right? So when you have an array, you can specify the base location by base R and use the offset to address the particular location in the array. And STR is similar, so you store the content of source register into this particular location in the memory. So this is particular assembly code. Is there any question?
الحمد لله.
Hello.
بخير الحمد لله. لا عندي كلاس.
Sorry, could you mute yourself? Who is this? Yes, so this is a particular assembly code. Here are the field values and the machine code. Hopefully the correspondence is clear for you. In this case, you have a base R here. You see 0, 1, 0 pointing to R2. In R2, you have a memory address. This is the base address that you use. You add it to this sign extended of this offset, 6-bit offset that you have. Again, very similarly, you load it to MAR in the first, then second read from the memory and load it to MDR, and then load it to destination register. In this case, is R1. Okay, and then address of the operand can be anywhere in the memory. In MIPS, as I said, we have limited number of addressing mode. Base+Offset is one of them. This is, for example, high-level code. We want to put a particular number into an array. We use, in this case, S0. This is, again, $S0 is one of those register in MIPS. And we have offset of 8. And then store it into S3. Or basically, this is the semantics. So you have a particular memory address is S0 plus 8. And you know that in MIPS, it is word addressable. And then you store the content of S3 into this particular memory location. These are the field values. And this immediate is sign extended to 32 bits. So this is, for example, a high-level code, like 3 lines of code. The semantics is simple, right? So you have an array specified by A. You want to retrieve the first element of the array, put it into A, do some operation, A plus B minus 5, and then store this content of C into another array in the first element of B in this case. So you can specify these inputs by registers, as you know, in assembly code. And this is the first one of very simple, basically, assembly code beyond 1 or 2 lines of code, probably in this course that we are going to talk about. But as I mentioned, from the next week, next lecture, we are going to cover more complex, more interesting assembly program, or more interesting logics that you can implement with assembly. So let's discuss how we need to proceed. So here, the first we need to access memory, right? So we have A0, we need to access memory. We know how to do that in MIPS. We have particular instruction, load word. So we know the base address of A, which is S0. Again, make sure you understand this. S0 is pointing to the base address of A. Okay, is specified up there in the MIPS register. And then we want the first element, right? So 0 is pointing to the offset, or the first element of this array, and we store it into a temporary register, in this case T0. Okay, so we load the content of A0 into T0. And then we need to add the content of A0, which was in T0, right? So we stored A into T0, okay? And then we add T0 to B, right? We need to add whatever we had, A to B, and then negate, and then subtract 5 out of them, right? So first we need to do this part. So here we use add instruction in MIPS. So we add T0 to S2 and store it into another temporary variable, T1 in this case, right? Because we need to store it in a temporary variable. Next, we want to subtract 5 out of them, right? So subtraction in MIPS, you can use add I to add a negative number to the previous value. You store this temporary T1, you add -5 to it, you store it into another temporary variable, and then here in T2 you have the content of the value of C in this case, right? So far we calculated the value of C. And next, you need to store the value of C into B0. So you have S1 here located, indicating the base address of B, the first element offset of 0. So basically you store word whatever you have in T2 register, which was C, and you store it in this memory location. Do you have any question about this?
So if you wanted to access like index n of an array, you need to do that index times the offset of that assembly language, like, or like what was it for MIPS, if I remember correctly, or Right. So if we want to like get index 2, we do 2 times 4, and then that would be the offset.
Exactly.
Okay, gotcha.
Because
Thank you.
it is word addressable, so you need to multiply it by 4.
Right. Okay.
Very good point.
I have a question as well.
Yes, go ahead.
So it looks like from that assembly code, you can store an array in the register, right? That's a 0. That's like a place
You can
attached to that register. So does that mean there can be multiple integers in an array stored in there in that example?
store the base address of an array. So where it points to the base address of an array, right? So if you think about the memory address, right? So imagine that you have a memory block. The first element of, or the base address is one memory location, which is indicated here by S1, right? So S1 pointing to the first element or the base address of this array, right? The next element would be located at memory location base R plus 4. The next one is base R plus 8. So S1 is a memory location pointing to the base R, or the first element of the array, not the content of the array. It's just the memory location.
So then S0, S1, S2, all the S registers are located far enough apart that in memory you can store the locations pointing to those arrays without them, like, what's the word, running into each other?
Yeah. So basically S1, S0, these are, these are like registers, right? So these are these registers could be the content of the register. I mean, depends on like however you want to interpret it. Could be a data point, could be a memory address, right?
Okay.
So
Okay.
not necessarily you do not, so you can do both, right? So sometimes you need a memory address, sometimes you need a data point. And in MIPS, these register are only 32 bits, right? So you could store a number, you could like store a pointer to the memory.
So you could have an array with a couple elements, and then the S0 would be containing a pointer to each of the points in that array. And you could label like 1 and it would go to the second location, stuff like that.
Can you repeat again, sorry?
So I'm just trying to understand the syntax now. You
Yeah.
have the 0 there and it goes to the first array location. If you did like a 1, it would go to the second. That first line L's starting to read at 0, S0. If you did a 1, it would go to the second location.
So basically, if you want to, because here it says that store word, so it retrieves a word, meaning that 32 bits, right? When you say two, so you know that in MIPS is word addressable. So the next word is located at base offset of 4, because each word consists of 4 bytes, right? So in order to go to the next word, you need to give the offset of 4 to go to the next memory address in word addressable memory. And next one again would be would be 8, is located as memory address 8 in word, again, word addressable memory. Is it clear or not yet?
I think so. I don't want to hold up the class any longer. Thank you for answering.
Sure. Yeah, I can explain after the class in more detail if needed. And this is the assembly code for LC-3, very similar to MIPS. The only difference is that you have different encoding for instruction. You have LDR, but very similar semantics to LW. In MIPS, you have add and you have STR. But essentially, these are almost the same instruction in LC-3 comparing to the MIPS, at least in this particular assembly code. Is there any question? Yeah, if there is any question, let me know. And we have also immediate addressing mode. So in this case, load effective address. We have this encoding, opcode, destination register, and 9 bits of offset. This is the encoding of the opcode for LEA, destination register. And in this case, to clarify, there is no access to the memory. The semantic saying that PC plus sign extended offset and load it into destination register. Noting that the content of PC plus sign extended offset is a memory address. So you essentially load or computed a memory address and put it into the destination register. So now destination register doesn't contain a data point, but instead contains a memory address. Right, so in this case, sometimes you want to put a memory address into a register because you want to retrieve that memory address later on by some other instruction using that particular register. That's the way how immediate addressing mode works. Like in this case, saying that we want to use offset -3 and destination register is 5. This is the encoding. So we use the offset and we add it to the incremented PC, and we store the content of this calculation, again referring to a particular memory address. This content that you see in the DR destination register R5 is a memory location. Is not a data. Is a memory location. But like this is the way how we can interpret it. In MIPS is also similar. But also has a interesting use case, right? In MIPS, LUI, load upper immediate. Again, in this case, loads a 16-bit immediate into upper half of the register. Register, you know that it's 32 bits. And for LUI, you have 16 bits for the immediate, right? Because you need some bits for the instruction itself, you need some bits for the register and so on. So you only have 16 bits for the immediate. So in this case, it has a very interesting use case. If we want to implement this this particular high-level code, right? In C, for example, if we want to store this number into A, we could use two instructions in MIPS in order to do that. First of all, we need to use LUI, load upper immediate. We use the first 16 bits of this number, 65E. We load it into S0. Once we have this content in 0, these 16 bits of this number, then what we can do is to OR these two numbers, basically whatever we have in S0, and use this OR I, use the other part of the number as the immediate in OR I, and OR them together in order to store this number into S0. So there is no other way in order to specify, because, and the reason, hopefully it is clear for you, this number is 32 bits. There is no way to have 32 bits as an immediate in MIPS, for example, because in total in MIPS you have only 32 bits for encoding instruction, and you need some bits for encoding instruction, destination register, and so on, and you only have left 16 bits for specifying the immediate, and that's the way how you can store 32 bits into a register using a using this as immediate value. So essentially, you use load upper immediate to use the upper immediate part of the number and OR it with the lower part of the number. These 16 bits, the last 16 bits of the number for F3C. There is a question. So will the 0x portion will always be what the assembly reads as a memory? Yeah, this 0x, you know that this is the way how you specify a hex number, right? In hexadecimal, you start with 0x. Yeah, that's right. So the machine recognizes that this is a hexadecimal number, and the rest are specifying the number in hex. so machine can interpret it correctly. Does it answer your question, Bobby? Good. And this is particular example. We can go through this. Like this is, for example, this is the content of the memory, for example, in LC-3. And these are the addresses of the memory, 30F6, 30F7, F8, F9, and so on. And each of these, and again, like at each memory location, you have 16 bits. Again, this is LC3. Memories have 16 bits. So the first 4 bits is used for encoding the instructions. Again, you do not need to memorize this instruction and their encoding, but you need to be able to, once you are given the table of instruction, you should be able to find the right instruction and associate that with the right instruction here, right? So, for example, the first line is LEA instruction. The second one is add, ST, and add, store, and LDI. So these are the encoding, and these bits number 0 to 8 is used as, again, the immediate for LEA. It really depends on the particular instruction. For LEA, 0 to 8 is the immediate. This is again 2's complement, right? So it is -3. And hopefully you are able to calculate how this is -3. So in 2's complement is easy, right? So you flip the bits and you add 1 to it. So when you flip the bit, bit number 1 become 1, the rest 0, you add 1, so in total you get -3. And since the bit number 8 is 1, obviously this is negative number. So this is the way how you can calculate this number. You have, like for example, for add, you have 14 here, for ST, and so on. So you can interpret this. And the semantic of these, let's also review this, what this means. So in the first line, again, this is LEA. So you have PC, you have immediate -3. The current PC, you know that when we are at this line, when we are looking at LEA, PC has incremented. So it's pointing to the next instruction, which is 30F7, right? So the content of the PC is 30F7 -3, which is indicated by the immediate, and this is the 30F4. This is what this instruction says, that you need to store this number into R1, which is indicated by these 3 bits, right? So this is these referring to R1. This is an instruction. The second one is add. So you have R1, which is this 3 bits, right? this is this source register, and this is the target register. So target register is R2. You add R1 plus whatever you have in the immediate 14, and this is in R1 you calculated previously 30F4 plus 14, and you put this number into R2. Very easy. And then the next one is SD. So you need to calculate memory address and store a number which is specified by this register number, right? So this register number is referring to R2. In R2, you have 0x3102. So you need to store this number into a memory address which is indicated by PC -5, because this immediate is referring to -5. And so this says that whatever you have in R2 and it with R2 and 0, right? So this indicating that whatever you had in R2, like remove them and put 0 in R2. This is the way how you can erase the content of R2. And then once you did that, you add the R2 you add 5 to R2. Now R2 is 5. Hopefully this interpretation is clear for you. And then SDR indicating that you need to calculate. So here you have a register R1 plus this immediate is 14. So you need this memory location to store a number inside this, which was indicated by R2. And in R2, you already calculated and put number 5 there. So you put number 5 into this memory address, which is indicated by R1 plus 14, or more specifically 3102. Again, this calculation is this is simple adding, so this should be easy. And then next one is load immediate. This is the indirect memory access, if you remember. So you have immediate of -9, and you have PC. So you go PC -9, see what you find out in that memory location, and then store and go to another memory location and store whatever you find out there in R3. More specifically, after you do the calculation, you already know what is in PC. When you are here, PC is indicating the next memory address. So it's 30FD, right? So 30FD minus 9 is 30F4, right? In M30F4, you have here, right? So you remember in M30F4, you store 3102, right? So now you have 3102, you need to go memory address 3102. In 3102, if you remember here, you stored number 5. So you need to store number 5 there, and the final value of R3 become 5. This is the way how you calculate. So for example, one question in your exam could be giving you this table, plus obviously the way how to interpret this. So you do not need to memorize this, but asking you what is the final value of R3. And you need to go through these instructions one by one, and you need to be able to interpret these instructions and find out what's the value of R3 or other register might be. So these were the data movement instruction. Now we briefly will talk about control flow instructions. These are also important instruction when you want to write assembly code. And this control instruction, we discussed it before, like when we need to implement if then else kind of logic or while loop, we need this control instruction in order to do that. So we have some conditional branches and jump to implement we discussed about this, and specifically in LC-3 we have jump, and in MIPS we have J as instruction. So in LC-3 we have some concept is called conditional codes. Each time one of these registers, one of these 8 register is written. So these 3 single bits will be updated automatically by the machine. So again, every time that something is written to these registers, these specific bits that we'll talk about is automatically updated. So for example, and we have only 3 bits, right? If the written value in one of these registers, if the written value is negative, N is set, and Z and P are clear. If the written value is 0, Z is set, N and P are cleared, and if the written value is positive, P is set, and the other 2 are clear. And these are used for, again, for checking, and if the check is valid, it jumps to a new memory location. Branch if 0, for example, is one of these instructions, but there are also other variation of this as well. And this is the encoding, how the encoding looks like, right? So you have N, Z, and P as 3 different individual bits, and you have offset, because if one of these conditions are valid, then you want to jump into a particular memory location specified by the offset. Yeah, we discussed about these, and the semantic is that if N is set or P is set or Z is set, then if one of these valid, then the jump will happen. And the jump, the semantic of jump is very clear. You need to change the content of PC. PC is automatically incremented. So in order to do the jump, you need to add one number to it instead of like one. So this number is specified by offset here, but again, you need to, as always, you need to sign extend it in order to have these 16 bits as usual, and then put it back to the PC. So again, PC currently is incremented. Whatever offset you have, you add it, and then you put it back to the PC. And these are the variation, right? So BRN, BRZ, BRP, BRZP, BRNP, and also BRNZP. So depending on which one of these bits are set. And these are, again, to repeat that, are set depending on the value of that the machine write to one of these registers. Like this case, BRZ, this number, again, this specify offset here. And this is the way how it is implemented. So in this case, since this is BRZ, Z is 1, right? So this 1 bit is 1, and the Z bits is going to this AND. So hopefully you can read this logic gate. So these are AND gate. So again, this is BRZ. If this were a different command, these numbers here that you see would have been different, right? If this were BRP, Z was 0, P was 1, okay? If it were BRN, N here was 1, the rest were 0, and so on. Again, these 3 bits in this instruction, right? Then coming into this logic gates, and then going to these OR gates in order to determine the whether the jump should happen or not. Is that clear? That's a good question. So what if all N, Z, and P are 1? In this case, we have N, Z, and P when we have this particular BRNZP instruction. So BRNZP, in BRNZP, you have all of these set to 1. These 3 bits are set to 1, right? So what this instruction means? Any idea? So when we use this instruction, what would happen? Like, it's very easy. Just you need to put 1, 1, 1 here in these 3 bits in the encoding of instruction. So if we have 3, 1 here, what would happen? Any idea?
Well, if you didn't change the condition registers, then you know, 1 and 0 is going to evaluate to 0 to false. So only Z would go through no, because that would be 1 and 1.
I mean, in general, like this time this Z is 1, right? So this meaning that the last register that was written, it was written as 0 number, right? But depending on what was the last number that was written into one of those 8 register, this signal could have been different, right? But if you reason about it, like how many different possible variation we could have, right? The last value could be either negative, positive, or 0, right? That's the only possibility we have, right? So these signals could be the case that either n is 0, n is 1, or z is 1, or p is 1, right? Either of these could be 1. And if we have all of these 1, what would happen? You always get yes here, right? So if all of these bits are 1, this is the last one is or, right? So one of these at the end is 1, right? So you always get 1, and the answer become yes all the time, meaning that the jump will always happen. So this BRNZP meaning is an unconditional branch. So if you use this command, no matter what, this branch will happen. So this, you always jump into this memory location, whatever offset you specify in this command. Hopefully this is clear. But if we have BRZ, the only time that this jump will happen if Z is 1, meaning that the last value that has been written into one of those 8 registers should have been 0. If the last value that was written was positive or negative, the answer to this would have been no, right? So no jump would happen. Hopefully this is clear. How about this? Like if all NZP, these 3 bits are 0.
The jump will never happen because it'll always evaluate.
Exactly, the jump would never happen, right? So this is a no-op operation. So like when you want to specify a no operation, so like in this case, the jump would never happen. So this is a no-op operation. So no matter what specify as an immediate, no jump will happen. I think we went over time, so let's stop here. And next week we have more fun. We go beyond this single instruction.